Good evening, everyone. Today I am going to discuss about this NPTEL course entitled as a study guide in organic retrosynthesis problem solving approach. The course instructor for this course is Professor Samik Nanda from IIT Kharagpur, and I am Anirban Maiti from IIT Bombay. So I am one of the TA for this NPTEL course. So coming to the details about this course, so today's tutorial. So before coming to today's tutorial, so I just here add one slide about the syntones and synthetic equivalents, where you can see. So if we break any CC bond, or if we cleave any carbon carbon bond, carbon carbon single bond mostly by heterolytic cleavage, then that time we can see two syntons. Okay, two syntons, one is donor synton, another is acceptor syntons. Now what will happen, so if you break this cc single bond heterolytically, then one carbon atom will take the will take two electrons from that bond, and another carbon atom will show then negative positive charge. Okay, so which so the if suppose if this carbon atom take two uh, electrons from this bond, then this carbon will show negative charge, and this opposite carbon atom will show positive charge, right? So the negative one will call as a donor synton, and this acceptor synton, so the positive partner will call as a acceptor synton. So here I have mentioned several examples of donor syntons, uh, also their synthetic equivalents, and also I have written the acceptor syntons and their synthetic equivalents. Okay, already we have discussed this previously. So coming to the real problem about retrosynthetic analysis. So first we'll see this example where you can see. So this is, if you see this molecule and we have to do the retrosynthetic analysis. So if you see this molecule, it is 6 and 5 member ring. It contains 6 and 5 ring, and if you see the connectivity between two rings, it is pyrocyclic. Okay, so this is a pyrocyclic ring. Okay, and also the five member ring is containing this alpha beta unsaturated ketone system. Okay, so how we can synthesize, or how we can plan the retrosynthetic analysis. So first, this we could get from this alcohol. Okay, so this is alpha beta hydroxy alcohol. Okay, so if we could get from beta hydroxy alcohol, that mean this beta hydroxy alcohol we could get if we do this CC1 disconnection. Okay, because there is some famous known reaction to get this beta hydroxy alcohol is known as aldol reaction. Okay, so we can think about aldol reaction. Okay, so here aldol reaction here, for forward synthesis here to here we can think about aldol reaction, or for retrosynthesis analysis, so this could be we could get from retroaldol. Okay, so anyway, so this is the one, two, three, four. One for dicarbonyl compounds, one for not diketone, one for dicarbonyl compound. So this is ketone and this is aldehyde, right? So now this from where we could get. So we could get from the CC1 disconnection, right? So this CC1 disconnection. Okay. Now if we do, or if we think about this CC1 disconnection, what we can get, what are the synthetic syntones we can get. So suppose this we could think about delta negative, and this carbon we can think about delta positive. So right here we have already, I have already written here. So then, so this will be the acceptor syntone, and this will be the, so the right side partner, it will be the donor syntone, right? So now we have to find out the corresponding synthetic equivalence for this synthons. So what will be the synthetic equivalence? So if you see, first we have written here the synthetic equivalence for this helium anion intermediate, that is nitromethane. Okay, so if we carry out the naive reaction on nitromethane derivative, then this carbon will get oxidized to get the carbonyl compound, right? And what about this? So this is, we have to think about the synthetic equivalent for this part. And now if you see, so this is the carbonyl carbon, and if we number this carbon as alpha and this is beta, so it is beta beta carbon we need positive. Okay, so that means we can get from alpha beta unsaturated ketone, right? So alpha beta unsaturated ketone, the beta carbon is electrophilic, so we could easily generate. So like that, so we have got the starting material. Okay, so synthetic equivalent for this acceptor synthon. Okay, now forwards, yeah, again how we can get this. So this is the olefin. Okay, so olefin we could synthesize from Wittig reaction. So this could we could get from Wittig via Wittig reaction by using this Wittig ylide and the cyclohexanone, this carbonyl compound. Okay, so this is the ylide and this is the carbonyl compound. So in forward synthesis, so this is the retrosynthetic analysis. So what will be the forward synthesis? So for our synthesis, we have to use this cyclohexanone and we have to carry out the Wittig reaction. So this is the ylide, Wittig ylide. Uh, yeah, if we treat this mixture in DCM under reflux condition, we could easily get this Wittig product. This alpha beta unsaturated Wittig product. Now, how we can get this Wittig So sometimes Wittig are commercially available, sometimes those are not available. So we can also think about the preparation of those Wittig So how we can prepare that Wittig okay, in lab from commercially available starting material. So now if you see, we need this carbon acid, like acetone derivative. So this side is acid, CH3CO. So CH3CO is okay. Now this side we can think about alpha chloroacetone. Okay, so this alpha chloroacetone, if you treat with PPS3 in toluene Arctic condition, room temperature, at room temperature, so what will happen? Normal nucleophilic substitution will happen at alpha carbon position. So then, so that means you get the corresponding Wittig salt, right? So this is the Wittig salt, right? So this is the Wittig salt. Now we have to generate the Wittig ylide. So if we treat this salt with base like sodium hydroxide in DCM, yeah, actually we have to dissolve this organic part, the salt part in DCM. Then we have to add the aqueous solution of sodium hydroxide like 2 molar or 4 molar. Then it will abstract the proton near alpha to this carbonyl group, and it will give this Wittig corresponding Wittig Okay, so like that we can prepare this Wittig alpha beta unsaturated Wittig Now, after getting this Wittig we can do this. We can carry out this Wittig reaction, and we could get this product. So, after getting this product, we have to do the on-for addition, right, with nitromethane. So, nitromethane pK is around 10. Okay, so the pK value, you should know the pK value of the acidic protons and the pK value of the bases also. pK value of bases means pK value of their corresponding what is that conjugate acids. Okay, so the pK value of nitromethane is 10 and dbu is around 17 18. Okay, so what will happen, dbu is non-nucleophilic base basically. So basically it will take the proton from this nitromethane and it will add to the Yeah, it will add to the beta carbon of this system. Okay, so what basically it will happen, the Michael addition or conjugate on for conjugate addition will take place. So after getting this nitro derivative, we can do the NAP reaction by using TiCl3. TiCl3 is an reductive cleavage of this reductive method to carry out this NAP reaction. So TiCl3 will convert this nitro to aldehyde. Then we have to do the aldol reaction, right? So aldol reaction we have to do, then we can get our corresponding product. Now this carbonyl compound, right? So this carbonyl compound from also we could get from this 1,4 addition of vinyl grignard to this same compound. Okay, same electrophile. So this electrophile we use here. So instead of using nitromethane, we could add vinyl grignard followed by so Johnson Lemux oxidation. Okay, so Lemux Johnson oxidation, that means in city you have to use osmium tetroxide followed by NaIO4 catalytic amount or 10 or 20 mole percent of osmium tetroxide then NaIO4 in the same reaction medium. We could easily get the diol formation from olefin followed by diol cleavage by using NaIO4, and we could easily get the same compound. Okay, same starting material, same 1,4 dicarbonyl compound. So now we have to do aldol reaction. So by using NaOH in ethanol RT condition, we could get the aldol reaction. First that beta hydroxy ketone followed by dehydration, we could get this 6,5 fuse alpha beta unsaturated ketone. Okay, compound, cyclic compound. Yeah, this is very interesting. Now coming to the next example. Okay, so this is a big molecule. If you see, so this name of this molecule is pyranophorin. Okay, so this is a pyranophorin. If you see, if you closely observe this molecule, so you can see this molecule having this alpha beta. So this is the alpha beta unsaturated compound. Alpha beta unsaturated carbonyl part is there. Also a lactone is there. So this is the lactone. This is another lactone, and here also down also alpha beta unsaturated ketone is there. Okay, and so this is a cyclic lactone. Okay, cyclic lactone ring. Now if you clearly observe that, so this is a symmetrical molecule. Okay, so you can pass C2 axis, so perpendicular to this plane of the molecule, and you will get the same. Okay, so basically, so this is a symmetry molecule. So how we can get, so we could think about the retrosynthetic plan first. So in symmetry, by keeping in mind the symmetry, we can think that this could be, we could get from these two starting precursor, and these two starting precursor are basically both the same. So via lactonization we can get our desired target molecule. Okay, so this is our target molecule, right? And if we do the lactonization of the same molecule, we could get easily this molecule. Okay, so due to this symmetry, we are having we are in our retrogenetic plan we are getting these two same molecules. Okay, basically this and this part are same molecule. Okay, now this from here we can get. So if we think about the this CC1 disconnection, okay, this CC1 disconnection, that time, so this carbon we will think about positive charge, and this carbon and carbon we can think about negative charge via Ohm Poulenc chemistry. Okay, so this Ohm Poulenc chemistry we will apply here in this path, and we can think about this acceptor syntone and this acylium and carbon ion as a donor syntone. Okay, so this donor syntone and acceptor syntone, what will be the corresponding synthetic equivalents? Okay, so if you see, so this is the acceptor syntone, right? So this simply you can get by attaching this carbon with halides, okay, like ClBrI. Okay, so you can easily generate the synthetic, you can easily get the synthetic equivalent. Now, what will be the acceptor syntone? So donor syntone, donor syntone, acceptor syntone is already done. We got the synthetic equivalent. Now, what will be the synthetic equivalent for this donor syntone? So we have to think about ampulang chemistry. Okay, so this is we could get from this. What will be the synthetic equivalent? This will be synthetic equivalent because this is having one acidic proton. We can easily generate carbon and here by abstracting this acidic proton, right? So yeah, so from where this we could get this synthetic equivalent for this acceptor syntone we can get here. Now from where we could get this synthetic equivalent, so we could get via Wittig reaction. If you see this synthetic equivalent is having this alpha beta unsaturated ester, right? So we can carry out do ester Wittig reaction. Okay, so already this ester Wittig preparation we have seen in last example. Okay, this with Wittig elite how we can get, we I have already shown you in last retrosynthetic analysis. Okay, so this will be the Wittig reaction will be the next reaction we have to carry out. Okay, now, so in forward synthesis, so first what we will do, if you see this aldehyde protected aldehyde we have taken, now we can think about deprotonation at this center. Okay, so deprotonation, so LDA already I discussed LDA earlier. What is LDA? LDA is lithium diisopropylamide, right? So LDA will abstract this proton and it will generate carbon and here. Okay, so this carbon and how it will happen in next step, the simple SN2 addition will take place and you will get the CC1. Okay, new CC1, this CC1 is you are getting. Okay, so now this aldehyde we are having, so this aldehyde basically we treat with this Wittig elide in DCM reflux, so we will get the corresponding alpha beta unsaturated ester. Okay, alpha beta unsaturated ester. So then what we have to do? We have to do the hydrolysis of ester to get this carboxylic acid, followed by I forgot to followed by deprotection of this OTHP group. Okay, in HCl, so we'll get this OH here. Okay, so sorry for mistake. So this is not OTHP. So this is the OH. Okay, so this is a deprotected OH. Okay, so OH we will get. Now this two molecule we will have. Okay, so two molecule we will have. So two molecule of this, what will happen? One molecule of carboxylic acid will do lactonation with this alcohol, and the alcohol of that carboxylic acid partner with that will form this lactonation at this side. Okay, so you will get basically, if you do the DCC coupling with two molecules of the starting material, you will get this lactone. Okay, cyclic lactone. Okay, now the next job is to remove this 1,3-diethane derivative. So that could be done by treatment with AgCl2 and HGO in methanol water. Okay, so and you got this pyranophorin minus pyranophorin. Okay, so this is how you can get this minus pyranophorin. Okay, so we'll see to the next example. We'll go to the next example. So the next example is, as you see, the name of this molecule is saccharin. Okay, so saccharin is an alternative. So it is a sweetener. Okay, it is sweetener, and it is an alternative of carbohydrate sugars. Okay, so those who are having sugar or having more carbohydrates in their food chart, so that they can use, like they can have saccharin. They can taste the sweet by using saccharin. Okay, so saccharin is an sweetener agent. So how we can synthesize in lab? So basically, we can think about this CN bond and SN bond disconnection approach. Okay, so that will leads to this carboxylic acid and sulfonic acid. Now, from where we can get this derivative? Okay, so basically, if we do the functional group interconversion, basically methyl to acid, we if we could convert, then we could get this. Okay, this carboxylic acid, right? So now from here we can get, so we could get this sulfonic acid derivative from this toluene via electrophilic substitution reaction at ortho position. Okay, ortho or ortho prime position. Now, so we have, for forward synthesis, we should start with the toluene, and we'll treat this with chlorosulfonic acid, right? So this chlorosulfonic acid, what it will do, basically it will do the electrophilic substitution reaction. Now, what is the chlorosulfonic acid? So if you draw the chlorosulfonic acid, it is so which, okay, so this is the chlorosulfonic acid. Now the electrophilic substitution reaction, what will happen? So this will add to this sulfur, and this chlorine will leave, right? Because chlorine is leaving group, chlorine will leave. But if you think this chlorine will leave, that is wrong actually. Okay, what is happening here? This chlorosulfonic is acidic, so it will dissociates H plus ion. Okay, H plus ion, and this H plus ion, what will happen? This alcohol, so another molecule of this chlorosulfonic acid will abstract this O, this H plus proton, and it will form OH2 plus. Okay, now if you see in electrophilic substitution reaction, this molecule will react. Okay, and it will leads to the elimination of this water, and it will give these two molecule. So this sulfonyl chloride derivative, so now it can give the ortho product as well as para product. Okay, so this is the para product, this is the para product, and this is the, so this is the para product, and this is the ortho product. Okay, now we need the ortho product, right? So what is para product also is very much useful reagent. So the name of this para product is, basically if you see, so this is 4 methyl sulfonyl benzene sulfonyl chloride. Okay, so this is called tosyl chloride. Okay, paratoluene sulfonyl chloride. Okay, so tosyl chloride, So this is used as a to make alcohol to living group by treating ethyl chloride. You can make alcohol to OTS, so you'll basically make as the living group. So this para product also useful. Okay, so you can't throw this para product, so it is useful. Now this ortho product we got, whatever we got, that we can do the oxidation. Okay, first what we do, the elimination of chlorine, and you can install this amine. Okay, so first this SN bond disconnection approach, or SN bond in forward synthesis, obviously SN bond formation reaction to get this sulfonamide. Okay, so now oxidation of this methyl by using KMNO4 to get this carboxylic acid. Now basically you have to connect this CN bond. Okay, so by heating you can easily get this CN bond. So basically as this molecule saccharide, right? Yeah. So coming to the next example. This is the molecule. So and only one stereo center, it contains only one stereo center, that is S isomer. Okay, now the starting material also given, and in starting material this stereo center is R. Okay, so basically you need to do the functional group interconversion, where you have to get this benzyl ether and carboxylic acid in this side. Basically these carbons, that means this, yeah, this carboxylic acid to benzyl ether. So this side we have to change this carboxylic acid to benzyl ether, and this side we have to do this primary alcohol to carboxylic acid. Okay, so basically if you see this molecule, so this is this carboxylic acid and this primary alcohol derivative. So first we have to protect this alcohol with THP. Okay, so to protect this alcohol with THP, so we can use this DHP, dihydropyran. So this is the dihydropyran. So you can make the protection of this alcohol, and you can get this OTHP. So O tetrahydropyran or THP. Okay. Now next step is to reduce this carboxylic acid by using lithium aluminum hydride to get primary alcohol, and then if you treat this primary alcohol with sodium hydride as a base in DMF and benzyl bromide as an electrophile, you will get the OVN. Okay, benzyl derivative. This is benzyl ether. Now basically you have to deprotect this OTHP by using H3O plus or mineral acid, treating with mineral acid. We will get this corresponding alcohol, and if we do the Jones oxidation, chromium tetroxide, acetone, uh, pyridine, so you will get this carboxylic acid conversion of primary alcohol to carboxylic acid. Okay, so this is our target molecule, right? So we got our target molecule from this starting material. Any doubt? Okay, so the next example, so this is the next retrosynthetic analysis. So if you see this molecule, so this is one gamma electron. Okay, right? And you are having this allylic side chain in the gamma electron. So how you can synthesize? The starting material is given here. So from this carbonyl group here, so this is the starting material. and this is the target molecule. So how we can get? So we can think about the retrosynthetic plant. So forward synthesis basically we have to do. We have to take the starting material and do the LAS reduction to reduce this lactone, gamma lactone, to get this secondary alcohol and primary alcohol this side. Okay, so this CO bond will get cleave and it will give this alcohol at this carbon and primary alcohol at this carbon. So we will end up with this and then removal of THP protecting group by treating with mineral acid H3 plus. We will get this primary alcohol followed by this is the 1,2 diol, right? So 1,2 diol you can easily cleave by treating with NaI over in methanol water. You will get a aldehyde. Okay, so this aldehyde in situ what will happen? It will form hemiacetal. Okay, so it will form hemiacetal, and then we have to do oxidation of this lactol. So hemiacetal or lactol. So we have to do the Jones oxidation to oxidize lactol to lactone, and we got this lactone, right? So this is how we can convert this starting material to our digit target molecule, right? So coming, so we'll see the next example. Just a minute. Slide we have another molecule for retrosynthetic analysis. So this molecule we have, this is our target molecule. Just a second. So this is our target molecule, right? So target molecule, if you see, so what is this? It is having this 1,2 diol. So this 1,2 diol, one is primary alcohol, this is tertiary alcohol, right? So how we can think the retrosynthetic analysis for these molecules. This is very simple molecule. So functional group interconversion based approach. So basically we can think about that this we can get from this epoxide, because if we add hydroxide ion, okay, hydroxide as a NaOH or LiOH in, so that hydroxide base ring opening of this epoxide will give this 1,2 diol, right? So this so epoxide how we can get, so this epoxide we can get from this carbonyl carbon, okay. So I guess I will maybe you know knows or I don't know. So there is one methodology known as name reaction, basically Korey-Chaykovsky reaction. So sulfoxonium or sulfonium ylide base reagent, so that if you treat any carbonyl compound with sulfonium or sulfoxonium based ylide, you will directly get this epoxide. Okay, Korey-Chaykovsky reaction. So this methodology we can apply here. Now this carbonyl carbon we can get from this alcohol by oxidation, right? So in forward synthesis, if we see the forward synthesis, so what will happen? So in forward synthesis, if we have this secondary alcohol, so secondary alcohol, if we do oxidation, so we can use many oxidizing reagents like PCC, PDC, or IBX. Here we use DMP and DCM as a solvent. Okay, so if you use DMP in DCM, so we will get the oxidation of the secondary alcohol and we will get this carbonyl compound, right? Now, this is the main reaction here, Korey-Chaykovsky reaction. So if we have this methyl, this is called sulfoxonium. Okay, there are two ylides. So this is not ylide. If we treat this compound with base sodium hydride, that time ylide will generate. Okay, so now I will show another reagent. So this is sulfur, methyl Me, and this is CH3 carbon, CH2, and another proton. Okay, so this is, and the sulfur will bear positive charge. Okay, so this is the trimethyl sulfur, right? Trimethyl sulfur. If you treat this compound with base like sodium hydride, so that base will take this proton, right? So because this is more acidic proton, so this base will take this proton and it will generate basically this CH2 minus. Okay, so this CH2 minus, so CH2 minus and S plus, so minus plus in adjacent atom, so that is known as ylide, right? So this is the sulfur ylide. So now this is sulfonium base ylide. But if you have this sulfur double bond oxygen, okay, see if you have this oxidized sulfur, that time we will call sulfoxonium ylide. Okay, so basically again if we treat this compound with sodium hydride, so one of the proton base will sodium hydride will take one of the proton, right? So base will take this proton and this sulfoxonium ylide will form. Now this CH2 minus, so CH2 minus will attack to this carbonyl carbon and it will generate basically CH2 minus and SO2Me, right? SOMe2. So this CH2 minus, okay, CH2 minus will add to this carbonyl carbon and this CO bond will append so to give O minus. So basically you will get O minus and this is CH2, this is the CH2 and this is the S double one O and Me2, right? So what will happen in the next step? So this will get after addition of this carbon and you will get this intermediate, right? Now this O minus will add to this carbon and this CS bond will break. Okay, and you will get this epoxide. You can think, you can imagine, right? And what will be the side product? Side product will be the Me2SO, right? So side product is dimethyl sulfoxide, right? So this is the side product, DMSO, dimethyl sulfoxide. So you will get this epoxide. So this name reaction So this is a very famous reagent for this epoxidation of carbonyl compound. Generally, we know how to carry out epoxidation on double one, right? Olefin. But if someone asks to do epoxidation uh, in carbonyl compound, then how will do? So you have to apply this sulfonium ylide or sulfoxynium ylide chemistry. So by the help of this Korey-Chaykovsky reaction condition, you can get easily the epoxide product. Okay. Now what will be the next? So this epoxide we got. So what will be the next? So after getting this epoxide, basically we have to open this epoxide. Okay. So to get this diol, because this is our target. So and this is the epoxide. Okay. So if we so now this epoxide ring opening we can do via two process. One is this is the base mediated, and the second one is acid catalyzed. Okay, base in basic condition what will happen? So OH minus will act, OH minus that will directly open this epoxide, and you will get this O minus and alcohol, and O minus will take proton from water, so H plus from water, and you will get the diol, right? So this is the base catalyzed mechanism, and if you have base mediated mechanism, not catalyzed, and if you want to carry out acid mediated epoxide ring opening, that time you have to treat with OH plus, right? So H plus, so basically that H plus, so what will happen, it H plus, so this oxygen lone pair will catch first H plus. So now it will become this O plus, right? So after getting catching this H plus, it will become this OH and this O plus, right? And now water will attack. Okay, water will attack to this carbon, and then ring opening. So you'll get this OH2, and then H plus, elimination of one H plus, you'll get this 1,2 diol. Okay, so this is the mechanism. So you can see how we can get diol from epoxide, and epoxide how we can get from Korey-Chaykovsky condition from a ketone, right? So very interesting example. Coming to the next problem. So the next retrosynthetic analysis. So we'll here we will see, we'll do the retrosynthetic analysis for same molecule. Okay, but not from epoxide. Uh, yeah, not from epoxide. How we can think about another retrosynthetic analysis? So this is the target molecule, right? TM. So how we can get? So this target molecule we can get from this olefin, right? So this is the 1,2 diol we can think. So this is carbon 1, this is carbon 2, and this is 1,2 diol. So this 1,2 diol we can get from this olefin, right? So by 1,2 dihydroxylation condition. So this olefin now from where we can get? So very interestingly, this olefin you can get from carbonyl compound. This carbonyl compound. So now this carbonyl compound, if you do the Wittig reaction, okay, so methyl Wittig reaction, we will get easily this olefin. Now similarly, this carbonyl carbon, this carbonyl compound, how we can get? So we can get from the corresponding alcohol via oxidation. Okay, so if you see the difference between previous retrosynthetic analysis for this molecule, the major difference is these two steps, first this one and this one. So basically, previously we were thinking that this diol could be obtained from epoxide, and that epoxide we could get from this carbonyl compound. But here this intermediate is different. Here we are planning that 1,2 diol we could get from this olefin, this double one, and this olefin we could get from this carbonyl compound, and this carbonyl compound similarly we could get from this secondary alcohol via oxidation, right? So in the forward synthesis, similarly we have taken this secondary alcohol, and if we treat with this DMP oxidizing agent in DCM, what you will get? So we will get basically this oxidized product. So only one hydroxy group is there, so you'll get this predominantly this carbonyl compound, okay, cyclohexanone. Now this compound, if we treat with, so this is the Wittig reaction condition, okay. So basically if we have this methyl Wittig salt, so this is the Wittig salt. Now we have to generate Wittig elide. So if you see, this is the CH2. So this is the Wittig salt I am drawing, PPC plus and Br minus, right? Now, first what will happen? We are using this THF is solvent, tetrahydrofuran, and potassium tertiary butoxide. So the pK value of potassium tertiary butoxide is around 17, I guess 17. Yeah. So what will happen? This oxide. So this will abstract this proton. Okay. So this potassium tertiary butoxide will abstract this proton, and you will get this elide. Okay, so this CH2 minus you will get, and this is the elide. Okay, so this Wittig salt to Wittig elide we generated here. Now so this elide will attack to this carbonyl carbon, and at the end it will generate the oxaphosphate intermediate, right? So all of you know Wittig reaction how works. So basically you will get, so this oxaphosphate intermediate, right? Now decomposition of this oxaphosphate intermediate will leads to the olefin product, right? Because this PPC oxide will form, so this 2 plus 2 in retro of this 2 plus 2, so it will generate this olefin, right? So this Wittig reaction, it's after doing this Wittig reaction we will get this olefin. Now from olefin how we can get this 1,2 diol? So very common. So there are very common oxidizing agents known as osmium tetroxide. If we treat this olefin with osmium tetroxide reagent, we will easily get this 1,2 diol, right? Very common. So you can see for same molecule, so from same target molecule we can have different retrosynthetic plan, okay. So depending upon the reagent conditions or functional group presence in your molecule, we can plan different retrosynthetic plan, because sometimes what will happen, so we'll not have all the chemicals in our laboratory, okay. So if we have different retrosynthetic plan according to our source we are having in our lab, so we can carry out the DGR transformation to get the target molecule, right? So this is the benefit of having different retrosynthetic analysis. So what it is having, so it is a 6 6 fuse ring, and the left hand side it is having the alpha beta unsaturated ketone, okay. And you have another ester in ring junction, right? So this is a fuse 6 6 fuse ring, and you are having the alpha beta unsaturation with respect to this ketone. So how you can synthesize, how you can plan to synthesize this molecule, okay. So then plan mean retrosynthetic study we have to do. So how you can, so first retrosynthetic plan is that like this. Okay, so this bond, just a minute. So I'll, yeah. Yeah. So first this CC1 disconnection approach. Okay. So this CC1 disconnection approach, if we think, then what will be the possibility? Okay. So this is alpha beta unsaturated carbonyl compound, right? So we can think about aldol reaction. Okay. Aldol reaction followed by dehydration. Okay. If we think about aldol reaction, then what will happen? So we can think about this beta hydroxy alpha beta, so it is unsaturation. Now we can think this beta alcohol here. Okay, this beta alcohol here. So if you do dehydration step, then you will get this alpha beta unsaturated compound. So basically you have to do a aldol reaction, you have to carry out an aldol reaction. So aldol reaction mean you can have these two carbonyl compounds. So this is COCH3 this side, and this is another carbonyl compound. Okay, so basically base will abstract proton from this side, and then normal aldol condensation to get this corresponding beta hydroxy alcohol, then dehydration, you can get this compound, right? So the next disconnection approach what could be? So we can think about, so this CC1 disconnection. Okay, this CC1 disconnection. So if this CC1 disconnection we are, just a minute. Yeah, my slides are visible, right? Okay. Yeah. So so the next is this CC1 disconnection we are thinking. Okay, so this CC1 mean what will be the corresponding synthons for this CC1 disconnection. So we can think about positive charge here and negative charge at this carbon. Okay, so now negative charge this carbon means, so this is a active methylene compound. Okay, so if you see, so this is the active methylene compound, it is having highly acidic this CH proton. Okay, now if you take this proton by treating with any base. Okay, any base, and then if we do Michael addition to this, so this is methyl vinyl ketone. Okay, so the commercial name is MVK, vinyl ketone. Okay, so if we think about the this is 1,4 addition mean, yeah, 1, 2, 3, 4, yeah, 1,4 addition or Michael addition. So so nucleophile is so nucleophile we can generate from this active methylene compound. So first step is basically Michael addition, and second step is basically aldol reaction. Okay, so you can get easily this 6 fuse this alpha beta unsaturated compound. Okay, so so basically, so the this is aldol reaction, aldol condensation. Okay, more, it is more correct, aldol condensation, and this is Michael addition. The next disconnection approach is based on Michael addition. Right. So now we will. So this is the retrosynthetic analysis. So now we will see the corresponding forward synthesis for this molecule. Right. So forward synthesis. So we have to take this active methylene compound and methyl vinyl ketone, and we have to treat this compound with base. Okay. So base. This is the base, sodium ethoxide or ethanol. So in ethanol, so we can take. Okay. Mm, so then, so basically this base will abstract this proton. So this is the active more acidic proton. Okay, so base will abstract this proton. So now this carbanion will generate here. So this carbanion will attack to the corresponding methyl vinyl ketone. So this is having this alpha beta unsaturation. Okay, so this is the electrophilic site, more electrophilic site, delta positive. So this carbonyl will attack to this MVK as a 1,4 fashion, and you will get the corresponding. This is the allol. Michael addition product, right? Michael addition product. The next step is we have to carry out. So in same reaction condition, basically the reaction condition is same only. Okay, but the in same reaction condition in one pot, first Michael addition will happen, then in the same reaction condition allol reaction will also happen. Okay, so this base is already there in reaction medium, so it will take proton to from this side. Okay, so this proton it will take again, and it will undergo this allol condensation reaction. Okay, so it will generate this alpha beta, so beta hydroxy carbonyl compound. So now the next step is dehydration reaction. Okay, so yeah, next step is dehydration reaction. If you do heat, if you heat this reaction or this reaction medium, so you will get the elimination of water, and you will get the corresponding product. Okay, desired product. So now the reaction, so reaction in this reaction, two in one pot two reactions are involved. First is Michael addition. So this first step is Michael addition, and the second step is aldol condensation. Okay, so this reaction is discovered by Sir Robert Robinson. So that's Robinson. So that's why we call as Robinson annulation reaction. Okay, annulation mean formation of ring. Okay, if you heard anywhere that annulation happening, okay, annulation mean the formation of many rings. Okay, so you can see here one ring was there previously, and you are creating another ring. Okay, so this ring was previously there, and you are generating another ring. So that's why it's called annulation, and this is called Robinson annulation. Okay, so this Robinson annulation reaction mean Michael reaction followed by aldol condensation. Okay, now if you carefully observe, so in one condition only two reactions are happening. Okay, so in this first condition only Michael reaction also followed by aldol condensation, both are happening. So that's why we call this type of reaction, we like it's known as domino reactions or cascade reaction or tandem reactions. Okay, so the three names are there, but meanings are similar. Okay, so what does these domino reactions mean? So basically domino reaction mean you have to carefully design a multi-step reaction. Okay, you have to, for like multi-step reaction uh, is sometimes you have to design a multi-step reaction. How you can design? No, you have to think about one pot sequence. Okay, multi-step reaction in one pot sequence. So how you can design? Like you can design in such a way that the first step of this multi-step reaction will creates the functionality that will trigger the second reaction. Okay, and so on. Okay, so basically the first reaction here, if you see, the first reaction is generating two carbonyl compounds. Okay, so Michael addition is generating two carbonyl compounds, and the reagents are already there in reaction medium. So this Michael addition, after Michael addition reaction, you are having two carbonyl compounds. So in the same reagent condition, aldol product it will happen. Okay, so you have to design in such a way that the first step, whatever functionality will generate after the first step, so that will trigger the next reaction. Okay, so what is the benefit of this domino or cascade or tandem reaction? So there are many benefits, like it is more economical. Okay, and also environmental friendly. Economical, why? Because in same pot, in one pot you are doing two three reactions, multi-step reactions. Okay, so that is very interesting. So it is highly economical and also environmental friendly. Okay, so this is the, so Robinson evolution is an example of this domino or cascade or tandem reactions. Okay, so now you got an idea about this type of reactions. So now, so we'll see the next problem for retrosynthesis. Okay, so this is a simple molecule. Okay, so this is cyclohexanone. Okay, so six member cyclic ketone, cyclohexanone. So how you can plan the synthesis for this molecule, how you can think? So basically you can think like, so here the functional group is this carbonyl group, right? So this is the functional group CO. So how you can do, think of retrosynthetic CC1 disconnection? So you can think about this CC1 disconnection. Okay, so this CC1 disconnection, what will happen? Also this CC1 disconnection. Okay, so both CC1 disconnection mean we were thinking ki this carbon should be a delta positive charge, and this carbon should be a delta positive charge, and this carbonyl carbon, so that will be nucleophile, so that can act as a nucleophile. So that means carbonyl compounds you want as a nucleophile, mean you have to think about Ompulang chemistry. Okay, so basically Ompulang already we have discussed in last week. Also Professor Samik Nanda many times discussed the Ompulang chemistry in his talks. So Ompulang, how we can generate? Okay, so basically we, if we have the 1,3 diethane derivative of this formaldehyde, so we can easily generate ampulang from this compound. Like carbanion we can easily generate by treating with base, and then if we do, so now we are having this Rx and RCl, Ri and RCl. Okay, so this will act as a electrophile. Okay, so we will generate nucleophile from this compound, and we'll add these electrophiles into the reaction medium, and we can get the corresponding product after nucleophilic substitution reaction. Okay, so this is the retrosynthesis. And how we can generate this 1,3 diethane derivative? So this we can derive from this corresponding formaldehyde compound. Okay, so this is commercially available. So in forward synthesis, so we'll take the formaldehyde, right? So we'll take this formaldehyde, and then we'll, so in order to generate the ampulang derivative, okay, so we have to have that six member ring with this sulfur and sulfur. So how we can get? So if we treat this compound with 1,3 diethane, 1,3 diethane, so this is the 1,2,3, so this is the 1,3 diethane. Okay, and if we treat with Lewis acid, so we can easily get the protected aldehyde. So protection of this formaldehyde with 1,3 diethane, we can get this compound. Okay, so now I have mentioned the pK of this compound is 31. pK mean this proton we are thinking about. Okay, so this proton we are thinking about for pK values. Okay, now this pK is 31. So now in order to abstract the proton of this compound, okay, so we need to have a base who is having the pK value more than 31. Okay, so now we can use this n-butyl lithium. N-butyl lithium, this is an uh, alkyl alkyl lithium. Okay, n-butyl. So this is the 1, 2, 3, 4. Yeah. So this is the n-butyl lithium. So the pK of this n-butyl lithium is 50. Okay. So that means it can easily abstract the proton from this 1,3 diethane derivative, right? And if you treat, so first you have to take this 1,3 diethane in your reaction round bottom flask. Okay, then you have to add n-butyl lithium drop wise, and the temperature you have to maintain at minus 78 degree centigrade. Okay, so then, So after addition, after complete addition of n-beta lithium, so you have to wait for at least 30 to 40 minutes so to generate the carboanion, okay, so at the center, okay, and then you have to add this electrophile. So this is the electrophile. So it now, if you see carefully, it is having two Rx. Okay, so this C iodine and CCl. So first time, so if you think about the living group aptitude, which is beta living group in between iodine and chlorine. So obviously iodine is beta living group. Okay, so first, what will happen? The displacement will happen at this carbon. Okay, so and this carbon and this carbon bond will form fast in this condition. Okay, so you will get this compound. So now again another proton is still remaining, right? So this proton we can easily abstract by using again n-butyl lithium. So again we have to add this n-butyl lithium into this compound in THF. THF is a solvent. Okay, so ether, it is tetrahydrofuran. THF, we know, tetrahydrofuran. So if you add n-butyl lithium into this compound, again it will abstract this proton, right? And it will generate this carbanion. Okay, so now the second nucleophilic SN2 reaction will happen. So and you will get the corresponding this compound this pyrocyclic compound. Okay, so this is what, this is actually basically protected form of ketone. Okay, so now you can easily generate the corresponding ketone by deprotection of this 1,3 diethyl derivative. So this deprotection also known, so you can use any Hg2 plus salt, Hg2 salt, and you can easily deprotect this 1,3 diethyl, and you will get the corresponding carbonyl group. So this is our target. This was our target in previous slide, and now you can see how we can easily synthesize this cyclohexanone, this 6-member cyclic ketone from this formaldehyde. Okay, so very interesting. Now, so now what we will do, we'll do some other example, and we'll use the cyclohexanone. Okay, the next example. So starting material and target molecule both are given. Okay, in this example. So this is the target molecule, and this is propyl bromide. So this is the starting material. So if you just starting target molecule, so this is having this primary alcohol. Okay, so starting middle given. So how we can plan the retrosynthetic analysis? Okay, so basically we can think about the CC bond disconnection here. Okay, this is C bond disconnection. This is a single bond disconnection, and we could get this donor syntone, and this is acceptor syntone, right? Any doubt? Now, so these are the syntones. So now we need to find out the corresponding synthetic equivalence. Okay, so first is acceptor syntone. The synthetic equivalent will be the corresponding formaldehyde, right? So now the we have to see the donor syntone. So donor syntone, in turn, we could get from uh, this Grignard reagent. Okay, so this Grignard reagent. So this will be the syntones, and this will be the reagent. And what will be the synthetic equivalent? So synthetic equivalent would be the corresponding bromide compound. Okay, so we can treat with magnesium, and we'll get the corresponding Grignard reagent. Now, from where we could get this synthetic equivalent. So this also we have to do the synthetic analysis. Okay, so in this, so this we could get from this alcohol. Okay, by treating with basically PBr3, we can easily get alcohol to bromide, right? So if you see, so this is the alcohol. Now This alcohol we could get from via this 2cc1 disconnection. Okay, this 2cc1 disconnection, right? So basically these two left and right hand side partners are basically same, so these and these are same molecule, and this in middle one is this acceptor syntone, and both left and right sides are same donor syntone. Okay, so this syntones from where we could get, so this donor syntone, the corresponding synthetic reagents are this propyl magnesium bromide, and what will be the synthetic equivalent, so corresponding propyl bromide. Okay, and this acceptor syntone, so it will be met- the ester, corresponding ester. Okay, methyl ester of acetic acid. Okay, all right, any doubt? Okay, so next is how we can, yeah, so for our synthesis. Okay, so for our synthesis we have to take the starting material, and we will take this Grignard reagent. Okay, directly. So we'll treat this methyl acetate, and we will treat with this propyl Grignard with two equivalent. So ester Grignard addition to ester with two equivalent. So it will give addition of two nucleophiles. Okay, so you'll end up with these two addition. So this nucleophile and this nucleophile. So these two are R group. You will add to this carbonyl carbon, and you will get this tertiary alcohol. Okay, now the next job is to convert this tertiary alcohol to bromide. Okay, so we can use PBr3, and we will get this R bromide compound. Next is uh, we have to do this green we have to make it grignard. Okay, so by treating with magnesium in presence of catalytic amount of iodine and diethyl ether in diethyl ether as solvent, we can easily prepare this grignard reagent, right? So iodine, what we will do, iodine basically, so in magnesium surface, so it is magnesium oxide layer, sometimes it used to be there. Okay, so aerobic oxidation of magnesium surface, it leads to the formation of magnesium oxide, and that you can easily remove by using iodine. Okay, so this Grignard reagent already done. Now if you add this Grignard reagent to this formaldehyde, we can get this primary alcohol, our desired target molecule. Okay, right, any problem? No. Okay, so for this molecule, we have to think about the exact retrosynthetic plan. So the starting material, so this is the target molecule for this retrosynthetic analysis. So and so also starting material is given to you. So in forward synthesis, how we could convert this starting material to desired target molecule, right? So we'll see the forward synthesis. So if you see this, this is the lactone, the starting material. Now we have to do the reduction of this. So this is the alpha, beta, gamma lactone. So this is the gamma lactone, right? Gamma lactone. If we do the reduction of this lactone, so what we will get, basically we will get this cc1 disconnection, and we will get this secondary alcohol at this carbon and primary alcohol at this carbon, right? So you will see this is the primary alcohol and this is the secondary alcohol. Now so in your molecule, we so we have this diol. Now also we are having this tetrahydrofuran. So this protected alcohol, right? Yeah, so this protection, we need to do the deep protection by using treatment with mineral acid H3O plus. We can easily get a deprotected alcohol, the primary alcohol deprotection, by using H3O plus, and we will get this triol, right? Now if you see this triol, so this is the diol. Okay, so this diol is 1,2 diol. So this we can easily cleave 1,2 diol. It could be cleaved by using NaIO4 in methanol water. Okay, so we can easily cleave this 1,2 diol, and we will get this oxidative cleavage to get this aldehyde, right? So aldehyde we will get. So now this alcohol is already there in your molecule. Okay, so it will not exist in this form. What will happen, this alcohol oxygen will attack to this carbonyl carbon, and it will be in equilibrium with this equilibrium with this lactol. Okay, so this is called hemiacetal or lactol, as it is cyclic, so it is lactol. So now lactol, basically you have to do the oxidation of lactol to lactone by treating with this oxidizing agent, Jones oxidation condition, chromium trioxide, acetone, pyridine, the mixture of these three reagents, so that is zone oxidation condition, you'll get the lactol to lactone conversion. Okay, so this is our target molecule. So we can see how we can convert the given starting material to our desired target molecule by one, two, three, four steps. Okay, so four steps we need to convert this starting material to our target molecule. Okay, so next example is yeah, so this molecule, so this is the target molecule. If you see this molecule, it is having this primary alcohol. This is the 1 degree alcohol or primary alcohol at this carbon, and the starting material, if you see, so this is the propyl bromide. Okay, starting material also given to you. Now we'll do the retrosynthetic plan. So retrosynthetic plan, so first this CC bond disconnection we can think, and what will be the corresponding synthons. So synthons will be the like this. So this carbon can be a negative charge and this carbon can be a positive charge. Now if you see, so this, if this carbon bears negative charge, then it will be like donor synthon, and if this carbon bears positive charge, so it will be acceptor synthon, right? So these donor synthon and acceptor synthons are there. So now we need to get the corresponding synthetic synthetic equivalence, right? So synthetic equivalent for this acceptor synthon is this formaldehyde, right? So this is the synthetic equivalent for this acceptor synthon, and what will be the synthetic equivalent for donor synthon? So this donor synthon, if you see, this could be this could we could get this we could get from this Grignard reagent. Okay, or Grignard reagent. So this is the reagent, right? So what will be the synthetic equivalent? So synthetic equivalent, definitely you need to have this corresponding uh, bromide compound, right? So this will be the corresponding synthetic equivalent. So you can easily convert this synthetic equivalent to this reagent by treating with magnesium metal. Okay, so now this synthetic equivalent will do the retrosynthetic plan. Okay, so in next slide, so this synthetic equivalent we could get from this corresponding tertiary alcohol. Okay, so forward synthesis we will see how we can get. Now this tertiary alcohol, how we can get. So this tertiary alcohol basically this cc and this cc1 disconnection. Yeah, sorry. Yeah, so this cc1 and this cc1 disconnection. Okay, so basically we can think about negative charge here, negative charge here, and positive charge at this tertiary carbon. Okay, so this will be the acceptor syntone. So this is the acceptor syntone, and if you see the two donor syntones left side and right side both are same. Okay, so this is also propyl kind of propane kind of thing, this is also propane kind of thing. So these donor syntones are same, and you have acceptor syntone in middle. Okay, so how we can get this donor syntones and acceptor syntone. So this is the donor syntone we could get from this Grignard reagent. So this is one, two, three propyl magnesium bromide, and so this is the reagent. And what will be the corresponding synthetic equivalent? Of course, it is this propyl bromide. Okay, or bromopropane, one bromopropane you can say. And this is the donor syntone, right? So what will be the acceptor syntone? So acceptor syntone basically you can get from this ester derivative. Okay, so this is the ester compound called methyl acetate. Okay, so this is the methyl acetate compound. So in forward synthesis, yeah, in forward synthesis we will start with this methyl ester, and we will add two equivalent of this propyl magnesium bromide reagent. Okay, so what will happen? So it will add twice to this carbonyl carbon, and it will give tertiary alcohol, right? So tertiary alcohol we will get. So you can see tertiary alcohol we get, and with the addition of these two propyl side chain, now our next target is to convert this tertiary alcohol to bromide by using by treating with this tertiary alcohol with PBr3, and we can get this yeah, we can get this bromide compound, bromo derivative. So this is tertiary bromo compound. So what will be our next target? So next target we need to make this R bromide to corresponding Grignard reagent, right? So what we will do? So we treat this bromide compound or bromo compound with magnesium in presence of catalytic amount of iodine and in diethyl ether solvent. So you can get this corresponding Grignard reagent, right? So after getting this Grignard reagent, so our electrophile is already we have mentioned in retrosynthetic analysis. So it is formaldehyde, right? So it will add to the formaldehyde carbon, and it will give this primary alcohol, right? So this and if you see, so this is our target molecule. So this is our target molecule, and this is our starting molecule. Okay, starting material. So you can see, so we need one, two, three, four steps to carry out this conversion to complete this synthesis of this desired target molecule, right? So very interesting. Yeah, so coming to our next problem. So this molecule, okay, so just a minute. Yeah, so if you see this molecule, so this is having this five-member ring with this tertiary alcohol. So what will be the corresponding CC bond disconnection? So we can here already we mention here. So this CC bond disconnection, and this CC bond disconnection leads to two different syntones, right? One is this acceptor syntone, and this another is this donor syntone. Now this donor syntone we could easily get from the corresponding Grignard reagent, okay. And this acceptor syntone, so what will be the synthetic equivalent? So synthetic equivalent will be the corresponding cyclopentanone, okay. So now yeah, so this is the reagent for donor syntone. Now what will be the synthetic equivalent? Obviously the corresponding alkyl bromide. So this is the synthetic equivalent for donor syntone, and the reagent is this Grignard reagent. So now this bromo compound obviously we could get from this alcohol. Already we discussed similar problems in last examples. Okay, so this alcohol to bromo, we could easily convert this alcohol to bromide. Okay, now this alcohol, if we think about this CC bond disconnection, so this leads to this electrophile, not electrophile. So this acceptor syntone and this donor syntone. Now easily we could think about the synthetic equivalent is epoxide for this beta hydroxy carbocation type of acceptor syntone, and this we could get from another Grignard reagent, and this Grignard reagent what will be the synthetic equivalent, the corresponding bromide compound, okay. So it is very simple. Now we will see the forward synthesis. So just a minute. Okay, so the forward synthesis. So for forward synthesis we will have this halide compound, alkyl bromide compound, and we can treat with this magnesium in presence of iodine. We will get this alkyl magnesium bromide compound, right? So now epoxide ring opening by treating with this Grignard reagent, and we can get, so this Grignard reagent will attack to this carbon and it will open this epoxide, so you will get this primary alcohol. So now the next second we have to convert this alcohol to bromide. So we can treat with PBr3 in DMF and we can get this halide compound again. And again we have to make this bromide to Grignard reagent. Okay, so this Grignard reagent we make here. Now we have to treat with this cyclopentanone, this 1 2 addition. So this 1 2 addition of this Grignard reagent, and you will get this tertiary alcohol, right? So this is the forward synthesis. So this is how you can easily synthesize many more molecules by applying proper retrosynthetic plans, and mm, you can solve other complex retrosynthesis for other complex molecules also. Okay, so so you can see the glimpse, 1 2 3 4 5 steps we need to convert this starting material to target molecule, right? So we'll stop today. Thank you.